Okay, so we are talking about dynamic programming technique. It is a very powerful tool to solve most of the many optimization problem. It is very much useful for optimization problem. So, in the last, so we have seen the Fibonacci, how we can get the how we can use the dynamic programming technique to find the nth Fibonacci number. So, basically we have given a recurrence. So, we just try to write any formula in a recursive form. If we can write that, then we can apply the dynamic programming technique. So, basically dynamic programming is basically, so we call this as DP in short. It is basically the recursion. So, recursion means sub problem. So, we have a problem, so we reduce into a sub problems and then we use this solution of the sub problem reuse. Reuse means we have to memorize. So, there are two version of DP we have seen in the last class. One is memorization. So, we memorize the value once it is computed, then we use that reuse that value. Okay. So, that is the memorization. So, this is the basically. So, we memorize we store this into some dictionary, then we use it. Okay. So, in this lecture we will talk about another problem, which is basically the shortest path problem, single source shortest path problem. Single source shortest path. So, what is the problem? Problem is we have given a directed graph and we have some edge weight on the graph. So, that is basically W u v. So, this is the weight function where u v is an edge. So, u and v are two vertices in the graph. So, each edge is associated with a weight function W u v. So, then we have to find a. So, there is a single source, there is a source S, which is also another input. So, we have to find basically delta of S comma v for all v belongs to v. So, this is basically the weight of the shortest path from S to v. So, this is basically we considered the path from S to v, all paths. So, among them which is the minimum weight. So, that is the weight of the shortest path. So, we have seen the algorithm like Desta's algorithm, which will run for positive weight h, and then we have seen the Bellman-Ford algorithm. So, now we will look at, so these are all greedy approach, Bellman-Ford. Now, we will look at how we can solve this using the help of dynamic programming technique. So, for that, so you want to write this in a naive recursive way. So, the question is how we can get the recursive formula for this, how we can get the naive recursive algorithm to solve this problem. So, let us try to get that, then we can think to apply the dynamic programming technique. So, question is how to get naive recursive algorithm or recursive formula. So, the answer we do not know how to guess. So, answer is, so the guessing. So, answer is guessing, we want to guess. So, this is very powerful tool, guessing. We do not know the solution, we do not know the answer. So, guessing means we do not know the answer, answer. So, then what is the solution? Solution is guess, just guess, guessing. Okay. Not only guessing, but try all guesses, all possible guesses. So, try all guesses. This is sort of exhaustive search, and this is the beginning of the dynamic programming technique. So, we have a exhaustive search, then we will take the best one. I mean, we will try for all possible guessing, then take the best one with the help of DP technique. So, that is the idea. Okay. So, let us just try to. So, how we can get a naive recursive formula or naive algorithm for this single source shortest path. So, we want to find delta of s comma v. So, basically we have vertex source vertex s and we have another vertex v. So, we have some intermediate nodes. So, there are some vertices which are incoming vertex of v. So, these are the edges which are direct edge from going to v. So, these are the incoming edges which are going to v. Okay. So, this. Okay. So, now we want to find the shortest path from S to v. Now, we want to write this in a recursive form. So, suppose hypothetically, somehow we know some shortest path from S to u, just one node before v. So, these are all direct edge. Okay. Now, there are many direct edge, we do not know which will give us the minimum one. So, what we do? We try for all, and then we try for all, and then we guess, and that try will be doing by guessing. So, we try for all and then we choose the, I mean the. So, now the question is, by clever way or by we have to choose the best guess. So, that the DP will give us. So, then this plus W u v, this is the one of the vertex direct edge from 2 v, but we do not know which one. So, we have to explore all possible. This is sort of exhaustive search. Okay. So, this is the exhaust, but we do not know which one. So, suppose we have a, this is the sub problems. So, we reduce the problem into sub, this is the sub problems. Suppose hypothetically we have the solution of this sub problem, then we have this direct edge. Now we want to choose one of these will give the this shortest path, but which one we do not know. So, we have to try for all possibilities, these are the, so we have to guess which one. So, this is the guessing technique. So, if our guess is correct, then this will give us delta of s comma v. Okay. But we have to do this exhaustive search. So, basically delta of s comma v, this is the recursive formula, minimum among delta of s comma u plus w of u v, where u v is the direct edge from 2 v. So, these are all possible edges from v. So, this is the naive recursive algorithm, Okay. So, this is the naive recursive algorithm. So, is this good? So, this is the exhaustive search. So, this is basically, this is the exhaustive search we are doing. So, this is this the algorithm is good? No, this is not good, this is huge, I mean this is exponential. So, this algorithm is exponential algorithm. So, now we want to reduce this to be a polynomial with the help of guessing, and that will be done by DP method. So, that is the goal of the DP method. Okay. So, goal of the DP technique is we have a exponential, we have exhaustive search, it is a careful brute force. So, carefully we have to do the guess. So, that is the idea. So, this is the exponential time algorithm. So, we cannot go for all possibilities, we have to guess which edge will give the correct one, we will give the minimum one, that we have to guess. So, that is the goal of the DP. So, we have to guess that. So, that is basically that we are going to do. So, that is the DP technique. So, that we will do by memoization. So, that means we will once we, so we will use the same algorithm what we have done earlier. So, let us just write this. So, basically the DP technique is now guessing is added there. So, DP is basically we have sub problems, the recursion we have, this is basically the sub problems, and then what we have to do the memoization, and one thing is added now is guessing. Okay, we want to guess the correct path. Okay. So, now what is the delta of s comma v? Delta of s comma v is the minimum of delta of, this is the recursive formula, s comma u plus w of u comma v. So, this u v belongs to E. Okay. So, this is the basically now this formula. So, this is the naive approach, this is the exponential time approach. So, we want to use the memoize DP algorithm for this. So, that will reduce this from exponential to polynomial. So, what is that algorithm? Algorithm is basically, so we compute these deltas. Now, we compute delta of s comma v and we put it into a table. So, again if we want to compute it, so we first look into the table. So, if it is in the table, if it is in memo, then we return it. Otherwise, what we do? Otherwise, we compute delta of s comma v is equal to delta of s comma u plus w u v, and this is the sub problems. So, this is the sub problems. Now, once we compute this, then we put it into the memo. So, that next time if we need this value, we can reuse that. So, that is the idea. So, this is the memoization algorithm for this version. Now, what is the time complexity? So, we know the memoization. So, this we know the time for this type of DP is basically time is equal to number of sub problems into the time required per sub problem. So, that is basically into the time required per sub problem. So, this is basically time, total time divided by number of sub problems. So, this whole thing is basically rate of executing the sub problem. So, this is basically time per sub problems. Okay, time per sub problems. So, now what is the time then? So, time is basically so how many sub problems we have? We have v sub problems. So, number of sub problems is equal to order of V. Okay. Now, what is the time to solve each sub problems? How many guesses are there? The exhaustive search we are doing on the, so the basically the time for each sub problems is basically, so this is V, so this is basically possibilities. So, we are, so this is basically in degree of V plus 1. Now, if you take the sum, so total time is basically summation of, so we can put a theta over here, summation of in degree of V, in degree of V plus V for this one. So, in degree of V is basically order of E plus order of V. This is coming from Hansaking lemma. So, summation of, we know this, summation of degree of V is basically, I mean order of E. This is the Hansaking lemma. This is coming from Hansaking lemma. Okay. So, now is this algorithm work for any graph? No. So, unfortunately no. So, otherwise this technique is quite okay, because this will not work for, this is work for only DAC, direct acyclic graph, if there is no cycle. But problem is, if there is a cycle, then this method will fail. So, how? So, let us look at that. So, let us look at that. So, suppose we have a graph like this, S V, so A B, and these are the vertices, these are the edges. Okay. So, now suppose we want to apply this memorize algorithm, the guessing algorithm, and we want to memorize, suppose we want to compute S, this S to V. Now, to compute this, what are the edges going to V, in degree edges A. So, to compute this, you have to compute delta of S comma A, because there is only one edge going for this. Now, to compute this delta of S comma A, we need to look at number of edges, vertices, edges which are in degree to this. So, this is 1 only. So, for this we need to compute delta of S comma B. Now, here there are 2 edge incoming. So, to compute this we need to compute delta of S comma S, delta of S comma V. Now, delta of S comma S, this is the base case, this we assume 0, but this again is same as this one. Okay. Now, how to get this value? We haven't computed yet. See, this is now we are storing in the dictionary after getting the value, but this value is yet to get, we haven't complete yet. So, we stuck here, we cannot proceed further, because this is again a loop. So, this is the infinite time if there is a cycle. So, this will take infinite time, this is a, this we stuck infinite time if there is a cycle in the graph. That is the problem. So, this method will not work this way directly on the graph which is having cycle, because here we stuck, because how to get this value, we haven't computed yet. So, we look at the table, but it is not yet computed, because we have to compute, we are computing this and then we stuck in this way. So, then this is the problem. So, but to so how to overcome this problem? So, we know a technique. So, that is, suppose we have a graph with cycle. Now, how we can view this, how we can remove the cycle from the graph. Okay, suppose we have a graph like this, and there is a cycle. Now, we want to have a many version of this graph. So, this is the way how this is the time. So, this is the this is one version. Okay, so these are the connection. This is going here, this is going here. So, this is the we are just writing the copy of the same graph many times like this. Okay, so this is the 0th copy one time. Now, once we move from here to here, we just move from here to here like this. So, this way we can just avoid the cycle. So, but the thing is we are just increasing the, so we will try to, this is the acyclic graph now. Now, we will try to find the, we will apply this dp, memorize dp to get the shortest path on this graph. But there, so what is the problem with this approach? Problem with this approach is it will so it is increasing the number of vertices. So, if you write this delta k is s comma v is equal to weight of the shortest path from S to V, which use less than k edges. So, number of edges in that path is less than k. So, this is basically we know the formula, the minimum of delta of k minus 1 is comma v plus w of u v. Okay. So, this is the recursive formula we use. So, this is sort of its relaxation step. If you remember the Bellman-Ford algorithm or Dijkstra's algorithm, we have a relaxation step. This is sort of the relaxation step. So, now here what is the number of sub problem? Number of sub problems has increased by order of v square. Okay. So, the time complexity here is for this graph is basically order of v into e. So, this is the same time complexity of Bellman-Ford algorithm. Okay, but this is the way we just usually avoid the avoid the cycle in a graph. Okay, now we will just quickly summarize the DP technique. In general, there are basically 5 steps in any DP approach. So, let us summarize. So, we have seen a powerful technique which is dynamic programming technique, which is mostly used to solve any optimization problem, because it is basically reduce the space from we have a exponent, it is basically careful brute force. So, it is careful exhaustive search. Okay, so we have exhaustive search, we have exponential space. Now, from there we are going to reduce it to a polynomial space carefully. Okay, so basically it is a we for this technique we need to have a recursive formula or recursive algorithm, which is naive approach, which is recursive algorithm for which we can use the memoization version. So, this is basically guessing plus recursion, basically we need to have the sub problems plus the memoization. So, we will just store the value into the dictionary, so that when the next time we need that value we can reuse that. Okay, so the idea is to divide the problem into reasonably number of sub problems, and once we compute the value of the sub problems we store it, we memorize that, and then we will reuse that. And the time complexity is basically, we know this is basically number of sub problems into time per sub problems. This is the sub problems. This is the time per sub problems and this is the total number of sub problems. So, this is basically our. So, usually this time is theta 1 because we just mostly will do the table lookup. So, the total time is, if this is order of n, then the total time will be n. So, this again this analysis is amortized analysis. So, because we are doing the average case analysis, I mean on an average what is the time. So, this is the amortized sense. Okay. So, then we write the 5 easy step for any Diffie method. So, the 5 steps to dynamic programming technique. One is, first one is we have to define the recurrence, we have to define the sub problem. So, we should have that naive recursive formula, define the sub problems. This is the first step. Second step is we need to guess, guessing part of solution, we need to guess. Okay. So, that way we reduce this exhaustive exponential space to polynomial space. Okay. Now, we relate the solution of sub problems, relate sub problem solutions, and then we just recurse plus reuse plus memorize. Okay. Or instead of memorized version we can have a bottom up version. So, that also can be done. Then we solve the original problem. Okay, which is a combination of solution of the sub problems. So, let us take quick example. We have seen two problems in the today's lecture and last lecture. One is Fibonacci number, finding nth Fibonacci number, and today we have talked about the shortest path problem. So, let us just write what are the values of, what are the steps for these two problems. So, this is an example. So, we have, so this is basically we have seen the Fibonacci problem, Fibonacci, and then we have seen the shortest path problem. Shortest path problem. So, number one step is basically sub problems. So, what are the sub problems? Basically, you need to find f k for this, for 1 less than k less than n. This is the sub problems for this. And what is the sub problems for shortest path? We need to find delta of s comma v. So, this is basically, so minimum from s to v, which is used at most k number of edges. So, this is somehow hypothetically we know the answer up to the sub problems. So, that is the things. So, what is the number of sub problems here? This is n, but this is here is v square. Now, the guessing step. Guessing step is, here we do no need to do any guessing, nothing. So, the choice is 1, and here we need to guess, because there are how many vertices are coming from other, how many in degree. So, this is basically in degree plus 1. So, this is basically h into v. So, this is basically in degree. So, this is in degree plus 1 and then we have a recursion. So, for here we know the recursion f k is equal to f k minus 1 plus f k minus 2 and for here we know the recursion delta of k s comma v is the minimum of delta of k minus 1 s comma u plus w of u comma v. Then we need to check the topological order for DAC topological ordering and then we have the solution for the original problem which is going to use the. So, this is basically f n and here it is delta of s comma v. This is basically delta of v k minus 1 s comma v. So, this will take order of 1 time and this will take order of v times and there are. Okay. So, this is the 5 basic step for any DP problem. So, this is we have jot down for two problem like Fibonacci number and the shortest path problem. Thank you.